Okay, it's with great pleasure that we welcome back Ned Wright to the CFA again. It's great an honor for us to have him back again. So welcome, Ned. Ned received his AB degree from the physics department here at Harvard, and also his PhD in the astronomy department here at Harvard. He was also a junior fellow in the Society of Fellows, and then after leaving Harvard, he went to MIT, where he taught for a while, and then in 1981 joined the faculty at UCLA, where he is currently a professor of astronomy and astrophysics, and he holds the David Saxon Presidential Chair in Physics right now at UCLA. His research interests are in infrared astronomy and cosmology, and he's had a very distinguished career in both those fields. He did his PhD thesis using the 1 meter balloon-borne far-infrared telescope, and made the first far-infrared maps of many H2 regions in the galaxy. And I know that, and I'm sure Ned still remembers all the good times he had in the middle of nowhere's Palestine, Texas. Right, Ned? Yeah.
It's got lots of restaurants.
Oh, God. After that, he joined the COBE team, the Cosmic Background Explorer, and was very influential in the success of that mission. And for that work, he won NASA's Distinguished Scientific Achievement Award, and also he won the Gruber Cosmology Prize, which is awarded to the COBE team. And he followed that then by working with Spitzer, where he was interdisciplinary scientist on the Spitzer Science Working Group. And following that, he worked on WMAP, which mapped the fluctuations in the cosmic background radiation, and did it to a much higher degree than COBE did. And then following that, he was PI on the WISE experiment, which is a wide field infrared survey explorer, which mapped the entire sky, and has been a very, very valuable source of catalogs for infrared astronomy, and we'll hear about that today. I just wanted to also bring your attention to Ned's website, which has a very interesting tool called the Cosmology Calculator. It's really, I use it quite often, and also to bring your attention to his cosmology lectures, which are very, very excellent on his website. Ned was also science editor of astrophysics journals in the 90s, and he was also UCLA's Center for the Study of Evolution and Origin of Life, the Distinguished Scientist of the Year for that organization. He's also a fellow of the American Association for the Advancement of Science, a fellow for the American Academy of Sciences, and also a member of the National Academy of Sciences. So it really is a great honor to have Ned with us and to hear about the results from WISE. Ned?
Okay. Thank you, Giovanni. Yeah, Giovanni was a great advisor back when I was a graduate student, but and he knows all about this telescope, which I will show in the next slide. So here we go. So this is a slide that I showed in 1976 when I was giving my thesis colloquium here. So there's the 102 centimeter balloon-borne telescope with the Harvard pennant flying. And this is a page from my thesis showing our map of W3 and W3OH that we made.
That's also you.
Well, that's me, yeah. I had more hair then. But with WISE, we've advanced from having 4 pixels, which is what we had on the balloon-borne telescope, to having 4 million pixels. And so this is region W5, W4, W3, and I superimposed my map right here. So it actually shows real structure on the sky, so it's not crazy, but the resolution increase is amazing. So when we were thinking about WISE, we were trying to figure out how to get a good survey of the large area of the sky. And basically what we figured out is that you need many beams. So you need to have a lot of pixels, but and you also need low background. But the only other thing that matters really is the area of the telescope, which is expensive. So we decided that we would come up with a small telescope with a wide field of view, and that's the Wide Field Infrared Survey Explorer. And so we went up into space, which of course is expensive to do, but worth it, because we could get an infrared background from the telescope emission that was 2.7 million times smaller than it is on the ground. 2.7 million, that's a huge factor. Now, if you have a diffraction limited, background limited system, et cetera, you actually gain in integration time like d to the fourth. So if you have a larger diameter for a telescope, 2 times larger gives you 16 times shorter integration time. But because we have 2.7 million times lower background, it takes a 10-meter telescope on the ground about 10 to 15 minutes to match our sensitivity. And so you could do a survey from the ground, but you would need 6,000 8-meter telescopes working in parallel to do it. So it really does pay off to go into space. And then, we're going to see, this is AFTA, otherwise known as WFIRST. It's not all that, it's not using this great background because it's a warm telescope. So I'm a little concerned that it will look terrible compared to JWST, which will precede it. But anyway, that's just a political thing. So the way we actually do our survey, is to take a picture every 11 seconds. So this is a very short time for a spacecraft to move and set up and then settle. And so what we do is we scan at a constant rate, and then we have a scan mirror that freezes the image on the array and then flips back. So it's just the little scan mirror that has to move and settle. And so we get a large field of view. We have 47 arc minutes on a side. This is a 1 million pixel array. And we get about 10% frame-to-frame overlap as we go around in one orbit. And then in 2 orbits, we come back and survey a slightly different area of the sky because there's about 15 orbits per day. This is shifted over by 4 arc minutes, a small part of 47 arc minutes. And with many orbits, we get a lot of coverage. And then over 6 months, we actually cover the whole sky with much higher coverage up here near the ecliptic poles than down on the ecliptic. But we get about 8 exposures on the ecliptic, even after allowing for South Atlantic anomaly. So in order to cool the detectors on WISE, we went with a solid hydrogen system. And this is not the standard liquid helium system, but solid hydrogen actually has a huge heat capacity. So it's more than 10 times higher per gram than helium. So you get a lot more cooling out of hydrogen, and it was cold enough. So we're operating detectors that have cutoff wavelengths at about 28 microns. And so you need to have them cold, but not liquid helium cold. So we were operating them at around 8 Kelvin for the most part. So for a space mission, of course, you have to test it. So you have to go through shake and bake, otherwise known as vibration testing and thermal vacuum testing. So people were very nervous about shaking a cryostat filled with solid hydrogen because it might break, and then you got all this hydrogen. And so what we did instead is built a thermal mass dynamics simulator. So this is the TMDS. And so that was used instead of the hydrogen-filled cryostat for the thermal tests and the vibration tests. Now, unfortunately, you'll notice the second bullet says the vibration test was successful on the second try. The first try, we broke it. And so we had to fix it and then try to figure out, we did figure out why it broke. And so in order to save the mission, we actually needed to reduce the vibration levels. And so we were able to put on a soft ride. This is a little shock absorber. So it's traditional in space missions to not have any vibration isolation. So it's like driving a car with no shocks and solid tires. So you normally wouldn't do that. So here we put in a shock absorber. So this is little, 96 little springy peanut-shaped springs filled with elastomer damping material. And this is pretty much bolt for bolt replacement for the payload adapter fitting. So it just bolts in. And so that was built very fast by CSA Inc. And we then were able to survive the actual shake test. So here is that thermal mass dynamics simulator sitting on top of the spacecraft. There's the soft ride, and here's a big shaker table. So we managed to save the mission that way. That was our one big emergency. So you always have reserve when you're planning a mission because you figure something's going to go wrong, and this is what went wrong for us. So we had Space Dynamics Lab building the telescope and cryostat, putting that all together. And so we had to do some focusing. We actually focused on the ground. So this is the setup for doing the focusing. And then we did a variety of testing with their infrared chambers for testing things. So we were able to get things tested. And I'd like to show this picture because it shows the, actually, it's the hydrogen lifetime test. So here's the cryostat, and we're testing on a big empty runway on a retired Air Force base. And the structure we're testing in has these fabric walls with a gap between the wall and the roof. So any hydrogen leaks would just go up into space. I mean, hydrogen in concentrations greater than 4% is explosive, so we didn't want to have it pooling anywhere. And so then we put the whole thing together. This is now not the TMDS, but the actual cryostat. You can tell by the color of the bipods there. And then the acoustic test. So we did the acoustic test on the actual cryostat. And here's a guy. So this is a big bank of speakers. And they're all concentrating, focusing on WISE. And a rocket launch is really, really loud. So you're not allowed to get closer than 3 miles to the launch site. And then when you see the rocket take off, you can just start counting off 15 seconds, and then after 15 seconds, a huge roar comes. So even though we had that one disaster, we didn't have 2 disasters. So we actually got to the launch site on the day that we had predicted. So this is August 15th, the date we were supposed to deliver to Vandenberg. And this is payload processing facility at Vandenberg. And this now is this add-on here, which I've sort of cut off for discreteness, is the NRO high bay. You see they do some big things. And then next to it, there's the East High Bay and the West High Bay. So we went into the East High Bay, and that's WISE sitting in the High Bay. So it looks pretty empty. But when we surrounded it by all the equipment that we needed to fill it with solid hydrogen, then we sort of filled up the high bay. So basically, when you're filling something with solid hydrogen, you need to be very careful to make sure it solidifies in the right place, make sure it's been converted from ortho to para hydrogen before you put it in the tank. And then once it's full, you have to keep it frozen. So we just kept it sealed off so there was no evaporation and kept it frozen. Okay. So here's WISE in a canister and then going up to the top of the launch tower, the mobile service tower. So this was on November 20th, shortly before Thanksgiving, on 2009. And I'd just like to point out me, Peter Eisenhart, and Amy Meinzer. So Peter was the project scientist, Amy was the deputy project scientist. And she's the PI on NEOCAM, which is a future mission I'll mention later. Okay, then once we got up to the top of the rocket, then we're sitting here. This is the smallest fairing for the Delta II. So you'll notice that there's a lot of air there. And the particular configuration of the Delta II could launch about 1,500 or 1,600 kilograms into a polar orbit. And we were actually only 661 kilograms. So WISE is a very small mission. It's what we could afford to build. And there's not really a wide range of launch vehicles available for small missions. And so you could say, well, let's launch a whole bunch on one rocket. But everybody wants their own orbit. And in terms of phase space, a polar orbit is as far away from an equatorial orbit as the ground is. So you actually save nothing by launching into space and then trying to adjust the orbit. So here we are up on the top of the rocket, and we needed to keep the cryostat cold because we had to keep the hydrogen frozen. And so that required that we take up these helium dewars. So you all have, well, not everybody, but I had experience with helium cryostats when we were doing that far-infrared balloon-borne telescope, and we usually had 25-liter dewars. So 25-liter dewar. This is a 500-liter dewar. And here it is with people around it. So it's going up to the top, and we had to take 2 of those up per day. So that was 1,000 liters of liquid helium flow, and would flow through cooling coils to keep the solid hydrogen frozen. So it was a labor-intensive operation staying on the launch pad. And then we launched on December 14th. So it's actually very close to the 7th anniversary of launch. So December 14th, 2009. So it's now just 6 days from then. Oh, and I meant to mention, this is, it's getting to be, the dark time of year, the solstice. This is actually, for the latitude of Cambridge, the earliest sunset. So it depends on your latitude. LA, we had it on December 4th. But up here, the length of day effect is bigger. And so it's the earliest sunset. So it was pretty dark when we launched, but you can see it. This was at 6:09 in the morning. The rocket lit up the clouds, and off we go. And of course, we had to have an infrared camera photographing it too. And then we got a picture from an amateur photographer, engineer at JPL. This was handheld, and it was taken from Tahunga. So it's about 200 kilometers away. So it's pretty incredible. And that's the rocket plume expanding into the reduced density atmosphere many miles up. Okay. So there's the sort of last picture of the launch. And by this time, the cryostat vent valves had already opened. Remember, we were sealed off, so that nothing could escape. No hydrogen could leak out. But we had to open it up so that it could evaporate in space. And so that was done automatically. And the advantage of doing that is that it prevented having a critical event review board. So you can save a whole review in maybe 2 or 3 days and all that. So that had already happened, and that was great. But then we had to separate from the payload. And we actually, NASA insisted that we have coverage of all these critical events. So separating a payload from the rocket, we had a little camera to photograph that. And it was supposed to send telemetry down to the ground station in South Africa. And this is what we got, nothing. So $250,000 went into providing that, and we got no telemetry at all. No video shows up if we try to click on the box. Okay, but then we did have a critical event review board for this releasing the cover. Now the cover was in front of the telescope, on top of the cryostat, and it had been designed, and it was slightly off center. So the center of gravity of the ejection axis, center of gravity of the cover was not on the central axis of the spacecraft. So when we threw it off, we kicked it in angular momentum. So it was slightly offset. And so here we are sitting in the ground operations center and watching the wheel speeds. And so the 4 reaction wheels all reacted to the angular momentum imparted by the cover departing. And then we also saw the cryostat temperature start to fall. So we were quite happy with that. We didn't have any other way of resolving things, knowing that it had happened. Okay, so with WISE, we have 4 arrays, each 1024 by 1024. And they're at 3.4 microns, 4.6 microns, 11.6 microns, 22 microns. So these are our 4 bands. And you can see that by covering a wide range of really log of wavelength, about a factor of 8, we see a wide range of physical phenomena. So you see interstellar dust, and you see stars. You can see a little bit of dust at the shorter wavelengths, but you're dominated by dust at the longer wavelengths. And what we're looking at here is one set of pictures, then the next set of pictures 11 seconds later, and the next set of pictures 11 seconds after that. And this color one is just a color composite from these 3. Okay, now I want to draw your attention to these 2 stars here. You'll notice that they reappear here. So that is the 10% overlap from frame to frame. And then this star here reappears here. So we do get continuous coverage going around from pole to pole, and then we cover the whole sky. And so then the next critical event was making NASA happy by releasing pretty pictures within a month after starting the survey. So that was one of our level 1 requirements. And so we released this picture of comet sighting spring, NGC 3603. And then M31. Now Spitzer has done a picture of M31 that looks quite nice, but the Spitzer one is close cropped around where the emission actually is. So Spitzer covered about this area. And WISE covered all of it, in fact, the whole sky around it. So this is a 6,666 pixel on a side picture of M31. This is the Fornax cluster of galaxies. There's only a few spirals that are forming stars. Most galaxies and clusters are, of course, ellipticals. And ellipticals, even though they're considered to be old dead galaxies by optical astronomers, are quite blue for WISE. So here we have, I'm going to sort of step out from closest objects that we looked at to the most distant objects we looked at. So the closest objects we looked at were other satellites. So these are high Earth orbit satellites as seen in the QA images. So these are the very quick look images. And there's a few things to notice. There's a little stub of red here. So the actual exposure time was smaller on the short wavelength arrays than for the long wavelength arrays. So they're not strictly exactly simultaneous. Also, there's a little gradient across the field in the exposure time because of the readout. But then you can actually find these on the Infrared Science Archive if you're interested. So band 1, band 2, band 3, and band 4, this is not a geosynchronous satellite, it's probably a GPS, but I haven't figured out what it actually is. From the length of the track, you can estimate how high it is. But that wasn't our science goal. And while we asked the Air Force for funding, they never provided any, so they didn't get to tell us not to look at Earth satellites. But we did want to study asteroids. So the next thing we were looking at was asteroids. Now we can use the size of the infrared flux of an asteroid to estimate its diameter. This is the radiometric technique for asteroid albedos and diameters. And it turns out that the albedo of asteroids, I'll show you later, is bimodal. Albedo distribution has 2 peaks that differ by about a factor of 6. And so if you don't know whether it's dark or light, you get the area, projected area, off by a factor of 6, and you get the volume off by a factor of 15 or so. So you get a huge error in the volume and hence the impact energy. Also, if you're only surveying in the optical, you're much more sensitive to the highly reflective ones than the less reflective ones. But by surveying in the infrared, you could say we're more sensitive to the dark ones, but actually the 2 peaks are not light and dark. They're pretty dark and really dark. So all asteroids are much brighter in the infrared than in the optical in terms of total power. And so when you're looking at the infrared, of course, you're seeing how hot something is. The surface brightness, you see Amy Mainzer has a cold nose. And one of those cups is full of coffee, the other with ice water.
Which is which?
But when we're looking at rock, idea of their temperature. And so even though these 2 rocks reflect similar total amounts of light, one big dark one and one little white one, they radiate very different amounts of infrared. And asteroids are quite bright. So they're actually, this is a very early movie made by Joe Masiero. It's got 5 main belt asteroids previously known. It's only about a third of the field of view, and it's 4 successive orbits. So you can see the red dots moving, the ones that are circled, and here's a non-moving red dot. So that's, on the ecliptic, is about the ratio of celestial objects to asteroids. Most of the 12 micron sources are asteroids. Now this leads to a lot of asteroids, so we obviously had to get rid of the asteroids when we were making our catalog, because we'd previously experienced with the Air Force Geophysical Lab catalog where they had rockets, so they'd only scan over an area once. A lot of the weird sources that were bright in the infrared but not detectable in the optical turned out to be asteroids. And so we needed to have multiple observations to separate the asteroids from stars and galaxies. And we figured we might as well use that data to study asteroids as well. So just to reiterate, here's a simulation of a couple of objects, asteroids with 1 arcsecond seeing in the optical, and this is what it would look like if you had a perfect telescope, space telescope, much higher resolution than the Hubble. So milli-arcsecond resolution would be typical for an asteroid. You can have a light one or a dark one, and they reflect the same amount of light. And if you look in the infrared, they're about the same surface brightness. This one's a little higher surface brightness because it's darker, a little hotter. And then when you look with WISE, which has a 6 arcsecond resolution, you can barely see the light one, but you pick up that big dark one very easily. So with that, we went off surveying for asteroids. And I'll just show a few examples here. This is our most hazardous one, at least in my opinion. So it's 2010 MU-112. So this is one of the really dark ones. And it's got this parameter, the minimum orbit intersection distance of 0.001 astronomical units, which means that its orbit and the Earth's orbit get closer together than the moon's orbit. Okay, so if it came around with exactly the right orbital longitude and the Earth's orbital longitude, then it would be closer to the moon. Okay, you might say that's the wrong longitude instead of the right longitude. So the closest approach is at about 1 million kilometers that we can predict easily within the next century, so in 2082. But the thing is, the diameter is about 600 meters. So this is a scary large asteroid, and the inclination is high and the eccentricity is high, so it's coming in, hot and heavy, 30 kilometers per second before it hits the Earth's gravitational field. So it's about 24 billion tons of TNT equivalent. So that's a big ouchie. Okay, so this is just an illustration of the fitting for the size. So we've got 3 thermal bands that are pinning down the temperature, and then you adjust the size up and down till you get the fluxes right. So you get a albedo from this, because we also have optical observations, of about 2%. So that means that it's actually reflecting, because the albedo is more concentrated back towards the sun, where optical observers are looking. The actual phase function is about 0.4, so this is about a 1% bond albedo. 99% of the radiation that hits it is absorbed. And then the sun, at the time of the observation, was over here in the asteroid sky. And you can see that this color temperature prefers a certain subsolar latitude. And so our histogram of solutions in a Monte Carlo Markov chain of where the pole might be is kind of a ring around where the sun is. And then we get a diameter that's between about 500 and 650 meters. But the best fit's up here. So the best fit seldom centered. So it's down there in this low peak. So I just, this year, had a paper published on the albedo distribution from all the NEOs that we observed with the 4-band Ys, when we had very good measurements of the color temperature of the asteroid from the 4 bands. And so we have 2 peaks. One is dark at 3%, and one is bright at 17%. And it turns out that for the NEOs that Wise saw, only 25% of them were in the dark peak. So that's, in some sense, reassuring. On the other hand, it means if you want to find 90% of them, you've got a much harder job doing it optically than in the infrared, because that 25%, is more than the 10% that you're allowed to miss. So in February of 2011, WISE got turned off for budget reasons, and also we'd done the whole sky twice, but then we got turned on again in 2013 by the Planetary Division in order to find more of these near-Earth objects. So it's been running as NEOWISE, that's Near-Earth Object WISE, since 2013. So here's where we had solid hydrogen. We had 2 tanks of solid hydrogen. One ran out, and then the other one was working extra hard, and then it ran out. And then we cruised up to about 75 Kelvin, passively cooled. But then we stopped commanding WISE because we were turned off. And we didn't actually have this data until we got turned back on again. And the spacecraft said, "Hey, where you been?" I've been running this thing for 30 months without any commands. And then we unloaded all the memory on the spacecraft and got this temperature history. And then since about mid-December 2013, we've been surveying again. So we're still going, and we're still getting interesting results about asteroids. And we're still getting interesting results about astrophysical objects, but they're not conveniently arranged where you've got the catalog and the summed images on a nice NASA website, or IPAC website in this case. So you have to do a little work. Now I'm going to show you some pictures with nice blocky coads, because I had to do the work, so I wrote a program that makes nice blocky coads. So we found an asteroid 2015 QM3 that has an orbit that's smaller than the Earth's orbit. The semi-major axis is smaller than the Earth's orbit, but it goes out at aphelion, it's further away than the Earth's orbit. So we found it when it was coming back in closer to the sun. And obviously it had to go out, had to be seen again when it was, or previously when it was getting further away from the sun. So I figured out from the preliminary orbits that it was only 50% further away at that time. So it seemed likely that we could pick it up by adding up the frames. And so I did that, and I found a red source. So here's, for MJD 57209, this was the uncertainty of the orbit based on the data taken in August and September. And here's a red source. It doesn't show up at all in the 3.4 micron image. And at 57, the next day, it shows up in the same relative position on the error ellipse. Doesn't show up there, shows up in the W2 image. So this was fairly clearly the asteroid. We found detections. By the way, this was very close to the galactic plane. So it was 2 degrees galactic latitude. Very crowded field, lots of stars. That's pretty much why it wasn't picked up in July of 2015, but rather in August of 2015. And so we got that and reported it at the Minor Planet Center, and the orbit uncertainty for July, of course, has collapsed because we know where it was in July. But the orbit uncertainty for the next apparition, where 2018, when it's going to get even closer to the Earth than it did in 2015, has been reduced by about a factor of 3. So it's good to get these extra observations. But we can also use this to figure out the size. So we've only got 2 bands now, and it's not totally dominated by thermal emission. So it's a little uncertain, but we can still try to solve for where the rotation pole is and how big the thermal inertia is, and come up with a histogram of what kind of diameters work. So it's about 250 plus or minus 50. Roughly speaking. So it's a big asteroid, but big enough to cause a lot of damage, but that's data that comes from the infrared. So basically you can, I don't know whether you can sleep better at night, but NEOWISE is protecting the planet again. We're about to stop though, so you have to watch out. So Chelyabinsk was only 20 meters in diameter, and now is 450 kilotons of TNT. And just to repeat, 2010 MU 112 would be 24 million kilotons. So it's a lot of tons. Okay, so now let's move a little further out in the solar system, not near Earth objects, but just planets. So Neptune, WISE saw Neptune quite well. So signal noise ratio at 3.4, 4.6, et cetera, 500, 6,000. So lots of signal noise. So we can definitely see Neptune. Neptune's got its own internal heat source. And so if it moves further out, it would be cooler and harder for WISE to see, but we could probably see it out to about 700 or 1,000 AU. Now this is relevant for Planet 9. So it's not far enough out to really exclude Planet 9, if you believe the orbit calculations. So that's okay, but it'd be nice to have a better infrared survey that went to longer wavelengths. So maybe a far infrared surveyor should be the next big mission, maybe. But then we have Pluto. So in 2010, we never thought we had seen Pluto. But I thought that we could probably pull it out. I mean, again, the problem is it's right in the galactic plane. So this is where Pluto was supposed to be, and this is all the stars around. But we could pull it out by doing a fairly complicated fit, where we allow for all these red point sources. These are the background sources, fixed celestial background sources. Or the blue, rather. The red are all the pixels that we collected. And Pluto was moving like this during the time that WISE was observing its area in 2010. And so then we can do a simultaneous fit for sources at the blue positions plus a moving source at the black position. And then we can do that. And then we can represent it. So here is a picture of the solution. So you can just see little shade moving back and forth. So Pluto's definitely there. I mean, it's certainly bright enough to pick up with WISE, but it was just confused by all those stars. And so you can figure out the magnitudes is about 14. So it's about where you expect in the albedos, you know, in the range 12 to 18%. Okay, so by the way, I tried this on IRAS, which is out at 96 AU. And it's about the same size as Pluto. But what happens, of course, is the brightness of a non-self-luminous object goes down like 1 over r to the 4th as you move out. So that's a factor of 81. And if you take 81 on 14th magnitude, then you get down to about 19th magnitude. And that's a little too faint for WISE. So I haven't got any detection on IRAS. But we do have detections on brown dwarfs. So these are objects that are not fusing hydrogen to helium. Jupiter's sort of a brown dwarf with 10 to the minus 9 solar luminosities. Low mass M star would be 10 to the minus 3, even 10 to the minus 4 solar luminosities. And a brown dwarf in here can be various luminosities, depending on how old it is and how heavy it is. So here's an old model, or a model of an old cold brown dwarf, so 400 Kelvin. You'll notice that this 4.6 micron peak fits exactly in the WISE W2 band. And that's not an accident. We designed the W2 band to be at that peak. And then we put the 3.4 micron band here, and as compared to Spitzer, Spitzer has a longer wavelength channel 1, right? It's 3.6 microns instead of 3.4 microns. And so Spitzer picks up this stuff, and we don't. So we expect it to be very dark in W1. And then HST has been observing brown dwarfs at 1.25 microns, 1.6 microns, these little nubs here. And so that's a tough way to do it. Actually, JWST at 4.5 microns is going to be 5,000 times more sensitive than HST, or W first AFTA. So you're just not accomplishing the science associated with cold brown dwarfs by having a warm telescope. You need to get to 4.6 microns. So the object of interest is the 4th closest star system to the Sun. It's WISE 085507-0714. And it's got a W2 magnitude of about 14. It has been picked up at shorter wavelengths by Kevin Luman. So at that 1.6 micron bump, it's about 9 magnitudes fainter. And at the 1.25 micron bump, it's 10 magnitudes fainter. So the colors are really extreme. And it's the least luminous known brown dwarf, and it could be a free-floating planet. The masses are in the planetary range of 3 to 10 Jupiter masses, depending on the age. And so it's quite an interesting object. So this is the object moving back and forth. It's got a proper motion of 8 arc seconds per year. So parallax is 2.3 parsecs. And it was, again, Kevin Luman was able to find it because he looked at the single frame detections very carefully. And you see this background clump? That made it look not as red as it really is. So it was just an unhappy accident.
Was the parallax measured trigonometrically from the images?
Yes. Best value comes from Spitzer images. But I thought it would be worthwhile to try this moving target photometry again, like for Pluto. And so, this slide's a little out of date. We now have 132 frames, but I've updated this one. So we've got a standard deviation now of 2.2 microjanskis. So that's very faint. So it's sort of a 2 sigma on a source at magnitude 19.6. So with a lot of frames and moving, so you don't have confusion noise to worry about, you can really go quite deep. This is from 132 frames. Okay, and here's another thing that Luman found. This is, it's more of an embarrassment for optical astronomers because it was first picked up on the Sky Survey in 1978, then picked up again in 1992, and nobody ever put it together. So it was only discovered because WISE observed it 6 months apart. And so it moved an arcsecond or so. And that was a very obvious motion. This is really bright. It's also close to the galactic plane. So there's a lot of beasties hiding in the galactic plane. So it's worth looking. And here's a very rapidly moving ultra subdwarf. So again, here it is on 2 mass. The Sky Survey, WISE. So Sky Survey once, Sky Survey twice, 2 mass, WISE. So it's going about 2 arcseconds per year. Oops, too fast. And here's another one. Well, no, it's not sticking. Yeah, there it is. Palomar Sky Survey, WISE. So people haven't found all the high proper motion objects that have been photographed by the Palomar Sky Survey. So then move out to nearby galaxies. Nearby galaxies are always fun to make pretty pictures of, so we've done that. So we have a big enough camera, and of course the field of view is the whole sky, so we can make nice pretty pictures. And for these Messier objects and other large nearby galaxies, we can get very good images of where they are. But we actually set out, one of our science goals was to do the most luminous galaxies in the universe. And so we actually found that objects which don't show up at all in the 2 short wavelength bands, but are bright in the 2 long wavelength bands, are very high luminosity galaxy-like objects. So here's one at redshift of 2.5. So this is one of the first ones we published. So this is a W1, W2 dropout, or they've got the name of hot dust-obscured galaxies, or hot dogs. With Spitzer, you can get those W1, W2 detections, and they're pretty red, but very red in the W2 minus W3 color. And then they go up to high redshifts. Highest redshift we found is 4.6-ish. That's this one. So here it is. Its luminosity is 3.5 times 10 to the 14 solar luminosities, redshift 4.59. Shows up brightly at 850 microns. So it's a very bright object. Fair fraction of the luminosity is probably coming from an AGN because it's not really clear. You seldom have a situation where you have a huge starburst and no AGN activity. They're usually mixed together. But we can find less buried AGNs easily enough. People like to find AGNs by looking in the ultraviolet because they're much wider spectrum than black body. Black body is a hump. And the AGN spectrum is the power law. And the power law goes up to the X-rays, so they're bright in the X-rays, they're bright in the UV, but they're also bright in the infrared. So you get a pretty clean selection by looking at W1 minus W2 redder than 0.8. That corresponds to about a nu to the minus 1 power law, F nu going like nu to the minus 1. And so these are AGNs, and then we can ask, how far out can we see an AGN? That depends on how bright it is, but here's the most distant known quasar, still, redshift 7.085. And it was discovered not in WISE, but in an infrared survey. And here it is in WISE for the, this is from the unWISE COAD. But then here's my blocky COAD, still there. So we can see a lot of quasars, several million around the sky. So it's quite possible to just find optical combinations of 3 and 4 or 5 and 6 or even 10 quasars in the same field of a multi-slit spectrograph. Okay, other objects that we found are in fact clusters of galaxies. We're very good at finding galaxies by looking at redshift, at W1. And so the 3.4 micron emission is primarily starlight, so the red and dead galaxies that you might have in clusters of galaxies show up very well. Remember that they showed up blue, so they were strong in WISE W1 and W2. And people have been following these up, finding holes for the Sunyaev-Zeldovich effect, and so we've got a range of spectroscopically confirmed redshifts around 1 to 1.3. And we expect to be able to do more of this if we could co-add all the data. This is a project called MaxWise, which I'll talk about a little more later. We haven't been able to do it, but Aaron Meissner has been doing it, and for his own uses, and not, it's not NASA doing it for the whole community, which is a little unfortunate, but it is getting done, and all the data is on the ground. Okay, so what's the future for WISE? This is the orbit rate. You see it's gone up about 1% in orbits per day, and that means that the size of the orbit has gone down about 0.2%. So we are gradually decaying. We're coming in closer to the Earth and getting deeper into the atmosphere, but the solar cycle modulates the atmospheric density, so we see these oscillations. And as a result, our right ascension of the ascending node is drifting off the desired green line here. So let me blow that up. So this is the deviation from what we want. So here's the end of 2016, and this is a projection. So basically, we're now a little more than an hour off. So instead of being at 6 p.m. on the terminator, we're a little past 7 p.m. Makes it a lot easier to spot WISE if you're interested in seeing satellites, but you have to go on Heavens Above and type in WISE on their satellite from a database page to find it. And so basically we've been shifting our scan pattern away from symmetric around plus and minus 90 degrees. So this is the shift for the 2015 summer, but we are scanning about 15 degrees away from 90 degrees, so about 104 degrees on the PM side, and at 90 degrees on the AM side of the orbit, just to avoid Earthshine as much as possible. So, astrophysics with NEOWISE, well, we wanted to do a lot of stuff, and we proposed several times, but we haven't been funded. So MaxWise is part of that anyway. So we could have had a better product, and the data are all on the ground, so you'll get it eventually. So the single frames are out for 2015, and we'll be releasing again all the frames we take to the end of the mission. which is probably going to be March 2017. And so then we'll be releasing that in June of 2017 or thereabouts.
Because
So,
of the funding.
what?
Because of the funding that you're ending in March.
No, because the orbit's getting crummy too.
That bad.
So we are definitely getting out of where we want to be. And now I want to talk about NEOCAM, which is a project that it's a discovery mission that's currently under review in the last stages of review. Hope it works. We have detectors passively cooled to 40 Kelvin. So we have two bands, essentially the WISE-W2 band and the 6 to 10 micron band. And so each of these has 16 megapixels, so a much bigger field of view than WISE, and a slightly larger telescope. And so with passive cooling, we have an infinite lifetime. And so we're hoping to get up, launch in 2021, and then find all the NEOs that might hit the Earth. So we'll track. So we'll look at all these things. We should discover about 100,000 new NEOs, of which about 20,000 were big enough to be potentially hazardous asteroids. We also expect to find about 8 million main belt asteroids. So planetary defense, yes. I don't know whether that's science or not, but we definitely want to understand what we need to do and how ready we should be to deflect asteroids. But we also want to study the origin and evolution of the solar system, and this has left its scars in the distribution of orbital elements of the asteroids, and how they're distributed in albedo versus orbital distribution is something that's of interest. We can also study the cometary gas production, because the 4.6 micron band is very sensitive to both carbon monoxide and carbon dioxide. And then if we actually were to run an asteroid retrieval mission, we could find the objects that would be easiest to detect. So basically we're scanning a very wide range of elongations. And for 140 meters, we can see things quite far away. So we actually detect things a very large number of times. So we will auto follow up our objects. Right now we have 3 objects on the NEOWISE has 3 objects on the NEO confirmation page, 2 of which have preliminary orbits, or very tentative orbits that are quite interesting, but they haven't been followed up by any optical observer. And it's been about 18 days. So I don't know when those will be retired, but they're just being missed. So we'll come back, we'll observe an object 4 times and then come back to that same part of the field of the sky after 10 days and observe it 4 more times again. So then we'll have a good orbit. It won't get lost. And we needed to get detectors that would work at 10 microns, so we've been working on those. We have Mercad telluride detectors that can operate at 40 Kelvin and observe out to 10 microns. And then we will get, if we don't do anything, we'll be discovering NEOs about like this. If we do LSST, which we're doing, we'll discover these, but if we do NEOCAM, we'll do this. Okay, and if we do everything, LSST and NEOCAM, then you actually get up to the 90% congressional mandate. Yeah, a little late, but yeah, it's an unfunded mandate. So. Okay, so I want to thank everybody who was working on WISE, and so these are the main partners. Space Dynamics Lab did a great job. Ball did a great job. They were in charge of the integration and test, and by God, they got it there on time. This is a Ball truck and a Ball driver, and it is backing up to the payload processing facility on time. So that's how we stayed on budget. If you stay on schedule, you stay on budget. So if you don't get messed up by too many disasters, then you can do it. Okay. So I'd like to stop there and say, well, we're almost out of time, and we're almost out of time with WISE because the orbit's decaying, but I'm glad to have this opportunity to present some of the results. Thank you.
Thanks very much, Ned. Any questions? Yes, sir.
Is it possible to say from the WISE catalogs how many, the relative numbers of brown dwarfs and very faint red dwarfs?
Very faint red dwarfs, well, there's a lot of them, but of course they're very faint, so there's not that huge number.
So the space you can sample is small.
So basically, the thing is, a lot of red dwarfs are very faint because they're pretty cold, and so the optical surveys aren't very sensitive. But when you're down around 2,000 Kelvin, sort of right at the brown dwarf edge, they're actually extremely red, so they don't show up in optical catalogs very well. But you know, there's many millions, and in terms of brown dwarfs, there's thousands. It's not that many. You can't see them that far away. In terms of quasar, millions. So the WISE catalog is about half galaxies and half stars, if you just go look at them with the spectra.
Any other questions? Josh?
What have you done, Ned, in the time domain? I saw on your slide of your original objectives, you had something relating to that. But
Well, the time domain is part of the MaxWise thing that we hope to get funding.
yeah.
And we haven't had funding to do that, but there have been efforts by people using the WISE archives. So actually, Josh Bloom had a student working on RR Lyrae stars with WISE data, because the WISE cadence is such that you get several, a dozen or so observations within a day, and that's good for RR Lyrae stars, but it's not good for Cepheids. But he actually found that an infrared period luminosity relation for RR Lyrae stars would give distances that were accurate to 1% across the Milky Way. So there's a lot of power in that.
Ned, would you fly solid hydrogen again?
No, solid hydrogen is too much of a pain. And also cryocoolers have gotten a lot more experience.
Yeah.
So if you wanted to be cold, I'd say cryocoolers. And if you want to be 40 Kelvin, you're definitely better off with passive. So passive cooling is, the method of choice down to about 40 Kelvin. And then below that, you want cryocoolers.
The Spitzer got down to 28 because we were there.
Yeah, Spitzer was hardcore though.
Yeah.
So easily down to 40 Kelvin. I said it was cheaper down to 40 Kelvin. But Spitzer was trying to protect their helium. They did a good job on that.
Ned, what's the sensitivity difference between the cold mission and the passive mission amongst the detectors that are working?
Essentially nothing. So they are, there's a few more hot pixels, but the actual noise performance is pretty much the same.
Any other questions or anything? No? Okay, let's thank Ned again.